Good morning, everyone, and welcome to this Computational Social Science Lab webinar. And today we are very honored and pleased to invite Professor Marcelo Medeiros from UIUC to give us a very interesting talk this evening for Marcelo. Okay, so let me just briefly introduce Marcelo. He is the professor of economics at UIUC, and he personifies this theme of our Computational Social Science Lab. So he has the background of training with EE, electrical engineering, and now his research has a very broad interests in econometric theory, machine learning, causal inference, financial econometrics, and so on. He has done a lot of fundamental and important work in the econometrics, high-dimensional statistics, with applications in causal inference, forecasting, finance, and so on. So today, Marcelo will give us a very interesting talk on the very important question of high-dimensional modeling. So as we know, when you have high-dimensional data, you consider this modeling of either a dense model, such as the factor model, or sometimes people assume sparsity structure in the model. It seems like in the beginning, right, these two are distinct models that people use on different purposes. But today, Marcelo will give us a new perspective of the bridging the two models, right? So it's a very exciting, very nice work. Now, please join me to welcome Marcelo to give this speech. Marcelo, now it's your time.
Thank you very much. Thank you for the very nice and kind introduction and to summarizing so well the paper. This is a joint work of Jianqing Fan from the Operations Research and Financial Engineering Department at Princeton, and a former PhD student of mine, Ricardo Mazzini, who is now at the Center for Statistics and Machine Learning at Princeton. Ricardo is moving to UC Davis this year, so he's going to have a new affiliation. Okay, so the idea is exactly this. About I think the title says everything. We want to show you that it's possible to put together these two worlds, like density with sparsity. They can coexist. Okay, we were not the first one like to advocate this possibility, like to combine the two things, but we believe we are the first ones like to derive theoretical results on how we can bridge these two things. Okay, it's not the definite only way to do that. One of the possibilities that we think it's a nice one, and hope you also will find it interesting. But we provide a methodology that's very simple. Okay, you're going to see that the method itself is very simple, but the method comes with some theory where we show what exact objects we are going to estimate and how precise we are going to estimate, and if we can trust our results or not. Okay, and also I'm going to show you how to conduct inference, how to run tests on high dimension structures. Okay, and for this we will need some new theory. So there's a lot on the paper. Of course, it's impossible to cover during the duration of a webinar, but I'll be very happy to discuss more about that if you wish. The working paper is available on archive. There is a hopefully final version of the working paper coming out in the next few days. We are just wrapping up the revision. And that's it. So let's move forward, okay? So there's this big boom on big data in economics, right? So you see a lot of recent papers talking about that on large data sets, right? In economics. And we all know that when it comes to big data, standard econometric methods fail to handle such data. Okay, because usually you're going to have potentially more parameters to estimate than the number of observations that you have. Okay, that's what we call the kind of wide data set. Or sometimes you can have way too many observations that's difficult, like to invert matrices, so you end up in like in numerical problems. Okay, and that's what we call like the tall data sets. And we can have the wide and tall data sets, which would be a nightmare. Here we are going to talk more about the wide data set. That basically you have lots of parameters to estimate. Okay, and so in this case we have like curse of dimensionality. We can have post-model selection inference that will get worse with big data, right? And what's the solution? The recent past we saw lots of new techniques from like the high dimensional statistical literature and also machine learning methods, okay, that we can summarize broadly like in penalized regression, factor models, ensemble methods like bagging, boosting, and also nonlinear methods like tree-based models, deep neural networks, and the list goes on. We can spend hours here talking about methods to deal with these large data sets. Here are some revisions and papers that cover a lot of models, a shameless self-citation here, this survey that we have for specific case of time series forecasting. Okay? So let me give you the motivation of the method. Okay? Suppose that we have a collection of random variables, okay, that we going to group in this vector y. So we have n of those variables. Okay, so you can imagine these as different macro variables or volatility series from different companies, different returns from different firms, the GDP for different countries, whatever. You have these n variables, okay? And we want to uncover relations. And here I'm very general about what I mean by relation, okay? I'll be more specific in the next few slides. But here basically want to understand how these variables relate among themselves, okay? We may be interested in knowing how y1 depends on the remaining variables. It's a possibility. Or we may want to figure out what the covariance structure of those n variables, okay? And usually we want to uncover these relations from a sample of size t, okay? So two letters now, n and t. N is the cross-section dimension. Sorry, so the number of variables that we are looking at, okay? T is the number of observations of these n variables, so that we have over time. Can be time, can be other things, can space, right? But usually we think about the cross-section over time. Okay? The problem appears when n is much larger than t. That's what I'm going to call here high dimension. Okay, so we have more covariance than we have observation. Okay, so this will pose many problems. Even if you want to estimate like the covariance matrix of y, you can't have a covariance matrix that's positive, definite, for instance. Okay, so usually we need some restriction. Okay, because the data themselves will be silent about how can we uncover this structure. So we have to impose some restriction, okay, to estimate quantities of interest. Okay, so usually what we look for is a low dimension structure embedded in this high dimension problem. Okay, and what are the possible solutions? And that's where we have this density or sparsity thing. One way we can say, okay, let's write a factor model. Basically, all variables matter, but there is a kind of a driving force that explains how all those variables are related. So if I want to measure the importance of the variable 2, 3, 4, 5, n, and variable 1, all those n minus 1 variables are important for y1. Okay, so all variables matter, but the way we are going to model this dependence is through a driving force, and this driving force is what we call a factor or some factor. But usually the dimension of the factor is small, so there are a small number of those driving forces, okay, that can explain the covariance structure, right? The dependence structure, okay, among the variables. So we are going to model this relationship that we want to uncover via these small dimension structure that's a factor model, but all variables matter. That's why we call density, because basically this factor hits all the variables, and this creates dependence. Okay. Many papers in the literature, all the work by Jushan Bai and Turineng, and also from Forney, Halling, Lippin, Heiklin, and many other papers. There's a gazillion of papers in the literature advocating the use of factor models, dynamic factor models, generalized factor models. There are several different versions of a factor model. But what these models have in common is like impose this density. All variables matter. A variable depends on all the other variables. Okay. On the opposite side, we have this sparse structure that basically say, no, come on, not that all variables are important, just a few of them matter. So if I want to describe the behavior of my first random variable, y1, it's not necessary for me to look all the other n minus 1 variables, just a small group of them. And only among this large dimension set of variables, only a small group is really important. Of course, the challenge is to figure out what are the important variables, who are the important variables, right? There are many papers on that. I think classical one is the Lasso paper by Steve Shirani and the adaptive Lasso by Zhao, and then in time series, I have one paper on journal of econometrics, Koch and Calot, more recently, Babi, Balgaisov, and Trialkas. So there are many papers that still, every day you can see a new paper coming out about sparse models, okay? And there's this big debate, density or sparsity? Where's the silver bullet, right? What I should use that I solve all the problems, okay? And there is this recent econometrica paper by Giannoni, Lenza, and Vimicheri, where they basically construct a simulation study and they look at some data sets. They construct a Bayesian model where the priors can induce either sparsity or density, and they show some evidence that dense models describe better economic data. Okay? And you may say, oh, so let's forget about sparsity, let's keep density. However, there's another paper by Pava and Lopez who run the same experiment, but with a slightly different prior, and they show that sparsity it is the winner, that we should use sparsity. And in fact, Pava and Lopez, they show that depending on how you tune your prior, you can get one result or the other. So in fact, the whole debate is really dependent on the prior. So, and our take on that, because maybe there's no bullet, silver bullet, right? you cannot have, it's not that either you have density or either you have sparsity. It's problem dependent, and maybe you can combine both. So that was the idea of our paper, how we can use information in a smart way, right? Because in one sense, if we use factor model, we are going to discard some information there when we going to be clear soon. Also, when you are using sparse model, you're also discarding some information by saying that some variables are not relevant. So our idea here is like, okay, can we use all the information? Okay, of course, we cannot use all the information unrestricted, right? Because this will be impossible because we are in a high dimensional setup. But can we construct a methodology that allows the econometrician, the statistician, the data scientist to use all the information on the table, even in a high dimension setup? And the answer for that question is that we can do it, but we have to do it sequentially. It's a stepwise methodology. Okay, and with this stepwise methodology, we can use all the information available. So what we are going to do, two things: systematic way to unify factor and sparse model. Okay, so we are going to have econometric specifications which use all the available information. Second, we are going to derive an inferential procedure to test for general structures in covariance and partial covariance matrices in large dimensions. So everything is done in high dimensions. Again, let me repeat what I mean by high dimensions, that the cross-sectional dimension is larger than the time dimension. So n is much larger than t. Okay, so that's the setup. Okay? And why do we care? Well, there are many problems. I can list some. For instance, if you want to do some nowcasting forecasting, high dimensional setting, which variables you're going to include in your model, well, that's an important question. So, for instance, Stock and Watson in their papers, they advocate the use of dense models. Myself and some co-authors also use machine learning methods. There are recent paper by Andrew Babi and co-authors, the same thing. So using large dimensional settings to forecast and nowcast economic data. So our methodology can fit into this literature of nowcasting and forecasting. We can also use this technique to construct counterfactors with aggregated data, like in a synthetic control experiment. So I invite you to read a cousin paper of this one that I wrote with Gentry and Ricardo that was published in JASA last year, where we adapt the methodology that I'm presenting today to construct counterfactors and do some causal testing, causal inference. Okay. We can contribute also to the literature of network analysis, more specifically partial covariance networks, because I'm going to show you how to estimate and test structures in partial covariances in large dimensions. So we contribute to this literature put forward by Matteo Barigozzi and Mark Hallan and Christian Browland, Gudmundsson and Lugosi. And there's a huge literature also on this partial covariance network. Okay. So let me also give the flavor what we are going to do. Okay. So imagine that in a factor model, what we do is that we decompose, okay, the each of the variables in my cross-section. It will depend on factors, okay, plus idiosyncratic terms. Okay, and for this model to be identified, we put some restrictions on the factors based on the covariance matrix of the factors. Usually we assume that the covariance matrix of the factors are an identity. Okay. We have some restrictions on the lambdas, and we can or cannot, that depends on the factor model that we are considered, to have some restrictions on U, right? So we call lambda the loading, the U we call the idiosyncratic, okay? So the idea of a factor model is that instead of looking at the Y, so imagine that we want to run a regression of Y1 on all the other Y, Y2, Y3, Yn, okay? Instead of running this regression, okay, we are basically going to replace all those variables by the factors. Because basically here, what we are saying is that, okay, we want that most of the variation and the co-movements among the Y are driven by the factors. Okay, so all the relevant information is here. It's contained in the factors, and the idiosyncratic is pure noise that we can discard. So this whole literature on factor models, the literature is based on estimating F and using F in your regressions, in your models, but basically F is the most relevant term, and usually U is discarded. Okay, so we are leaving information on the table, because information, all the information that may be contained in the U's are usually left on the table. Okay, of course there are models that generalize that, but usually that's the case. Okay, and then we have the exact factor model when we say that all the codependence among variables comes from the factors, and what is left for the idiosyncratic is basically nothing. And then we have like idiosyncratic, the idiosyncratic covariance matrix is a diagonal matrix, so there's no correlation left. Okay, a generalized factor model leaves the sigma unspecified, but we need some kind of restrictions in a way that we cannot have much correlation left. So usually what we have is this low rank plus full rank decomposition of the covariance matrix of the Y, right? So the covariance matrix of the Y is lambda transpose, again, assuming that the covariance matrix of F is an identity, plus the covariance matrix of the idiosyncratic. Okay, so that's like in 2 slides, bird's eye view on factor model. Okay, so here, why we call this dense is because to recover this factor here, we are basically claiming that all the variables in my cross section, okay, loads on those factors, and those factors will create most of the codependence among the variables. Okay, so in a way, to recover this factor in a consistent way, we need that this factor affects most of the variables, so that's why we call them. Okay, and the low dimension restrictions, that the dimension of F is small compared to the sample size, such that we can replace the variables by F and run our analysis. Okay, on the other side of the spectrum, we have the sparse model. So what the sparse model will typically do? Define Y minus I as all the variables but the ith variable. So we remove one of the variables from the data set. Okay, and let's call beta I the coefficient of the linear projection of yi on this vector here on the top of the slide. Okay, so we want to run the regression to estimate this linear projection, but we know that we cannot do that without some regularization, some imposing some restrictions. And in order to interpret the resulting estimate, here we usually impose some sparsity assumptions, that either the number of non-zero betas is pretty small, much smaller than n, that's what we call strict sparsity, or the L2 norm of the betas is much less than n, that's what we call weak sparsity. Okay, so basically we are saying, okay, to recover the dependence structure among the variables, okay, we have to impose that most of the variables are not relevant to uncover this relation. Okay, so we are going on the opposite direction of the dense model. Okay? So we are basically imposing restrictions on the covariance matrix of the y on the omega. Okay, right? Okay, so these are the two initially opposite walls. How can we combine these, and why we want to combine these? So let's take the example of prediction. Okay, and let's assume that we are in a very fairy tale world where we can observe f. So we know the factors. Okay, let's assume that. And also, in this fairy tale world, we can observe all the idiosyncratic, but the idiosyncratic with respect to the unit size. Okay, so that's very idealistic world. Okay, but let's assume for now that's true. Okay, and our goal is to predict yi. Okay, the I of variable based on the information set that we have. And I propose you like three models. One model M1, okay, I'm going to try to estimate the expected value of yi given all the other y's. Yeah, but that's the information that I have. All the information that I have on the table. Okay. And two, I'm going to construct the expected value, but not using yi, because y minus I is large dimension, so this may be unfeasible. So I'm going to replace all the other variables by the factor that I'm assuming here to be observed. Okay. So here I'm the factor guy. Okay. And there's an M3 where, okay, so let's do the following. Let's condition on f, but also on all the other idiosyncratic. So instead of conditioning on y, I'm decomposing this vector y minus I here into f and u minus I. Okay. And then one question is, well, M1 or M2? Well, depends on the magnitude relative in terms of MSE of sigma, which is the covariance matrix of the idiosyncratic relative to lambda transpose. Okay, which one will have be the best predictor in terms of MSE? Okay. However, since the sigma algebra of y minus I and the sigma algebra of f contained on the sigma algebra of f u minus I, we can show, and it's not difficult to show, that the MSE of model 3, is less or equal to the minimum between the MSE of model M1 or M2. Okay. So the optimal is to consider M3. Okay. Of course, we have a problem here in large dimension because M1, imagine that everything is linear, right? How are you going to construct M1? Wow, run a regression of yi on y minus I, but this is a large dimension regression. So we have to use regularization. And if we want to derive theory in really high dimensions, you have to impose sparsity. Sparsity on what? we need to impose the sparsity on the relation between yi and y minus I. So we are in this sparse world. If we are using M2, we're going to run a regression of yi on map, where here we don't need to impose regression sparsity, any restrictions on sparsity, because F is low dimension. Okay, but this F here, this regression makes sense because we are basically saying that all the variables here can be well described by F. Okay, so this is a dense mode. M3, we are running a regression on a low dimension structure and on a high dimension structure, but with a detail. Now we need to impose sparsity restrictions not on the relation between yi and y minus I, but between yi and u minus I, the idiosyncratic. And the idiosyncratic, if you recall the definition of the factor model, is what is left after we remove the factor. So imagine that all the variables are strongly correlated, but this correlation comes from most of this correlation comes from the factor. So when we remove the factor, you are left still with some correlation, but not that strong. So we are going to impose restrictions on the relation of u. Okay, the relation between y and u with the idiosyncratic after removing the factor. Okay, so that's exactly what we are going to do. Our focus will be like to try to get M3. Okay, so and we are going to do this in a stepwise fashion. How we are going to do that? Well, remove the factor, take the residuals, estimate the relation among the idiosyncratic, combine everything together. Super simple. The problem is that we are going to do estimation after estimation after estimation. Is a sequential procedure. So in order to derive asymptotic results for the second step, we have to take into account the uncertainty of the previous step. Okay, so this propagation of uncertainty, okay, will make our life miserable, okay? And will make the theorem look pretty ugly. Okay, but I'm going to show you a very general result, okay, where we can clearly see how the hypotheses influence the results and what are the key factors that are important to trust in the end of the day the model, right? Okay. We do this for expected value, it's also true for projection. Okay, so let's move on to the method. Okay, so now, so this was a summary. So now let's look into more details about the model and make it a little bit more general. Okay, so what's our data set? We observe y and x. Okay, y are the variables that I have been talking all the time here, and we have n of these covariates y. Okay, observed at t periods of time. But we also have auxiliary variables, x. And x is a vector. So for each unit, each individual I have a vector x. That I'm going to assume here that's of fixed dimension, and it's the same dimension for every unit. Okay. So it's a k-dimensional vector of observable random variables. Okay. And then we have the following model. So the model that we have in the end of the day is like a panel model. So YIT depends on the axis, on this observed variable, depends on the factors, and then we have the idiosyncratic. Usually the factor model say, don't bother about you, your goal is to estimate X and F. We are saying, okay, you can be important to bring additional information, is where the sparse structure is, and you depends on this vector W. The W is a non-empty subset of this larger matrix here, this vector here, that contains all the other idiosyncratic at time t, and all the idiosyncratics, including unit I lag value. So you can have like dynamic model here. Okay. Motivation for that, I can give you several. Okay, which kind of data we expect to model here? Now, let's take finance models, empirical asset pricing, where Y is the excess returns over the risk-free rate of different companies. Okay, so I index company, T index month. What are the axes? Can be like observed factors, like the PAMA French factor. So the market return, high minus low portfolios, small minus big portfolios, momentum portfolios, name it. Okay, there are a zoo of portfolios or factors. They are here in X. They are observed values that influence the behavior of Y. But you may say, okay, but not all these factors are properly modeled. Okay, they may be misspecified. There may be other factors, right, influencing the movement of return, and those factors are not observed. Oh, send them to F. So F are all the unobserved factors that affect Y, the return, and use the idiosyncratic. So you remove the common factors that drives the co-movement between assets, but then you get the residuals of that idiosyncratic, and you want to explore how firms can be linked together after you control for the common shocks that hit the market, or the common anomalies that you have in the market that can be described by PAMA French type of factors or unobserved factors. So you are interested also in knowing the data here, how firms are linked. So it's one example. Another example, suppose that Y is a panel of, represents a panel of macroeconomic data, or a panel of inflation data for different countries. Okay, or a panel of economic output data for China, or for the US, or for Hong Kong. Okay, and X, you can say, oh, this can be a deterministic trend, this can be seasonal dummies, can be any outlier dummies. Okay, so are variables that you think can describe the behavior of this macroeconomic data. And then you have factors like economic factors. There are the huge literature on economic factors hitting the economy every day, every month. So these are the factors. And then you have the idiosyncratic, how these variables here are related among themselves. So you can cast in this way. So there are many applications where we can write down economic data in this fashion. Okay. So what we observe here, we observe Y, we observe X. We do not observe F, and we do not observe U. Okay? Of course, we do not observe the parameters, and we have to estimate. Okay, so our goal would be to recover the parameters, gamma, lambdas, and thetas, recover the factors F. Okay. Some comments here. The proposed model can be relaxed in several dimensions. Most our results are for projection models. So basically, going back here, this is the projection model. We are not giving any causal interpretation for the gammas, the lambdas, or whatsoever. However, it's easy to fix the estimation. I'm going to go where we can do this to make, for instance, the gamma to have causal interpretation. Basically, we are going to replace the first step. The first step in our methodology is an OLS. We can replace the OLS by ID or Pesran CC estimation method, and all our results continue to hold. Okay. We can make the relation with X nonlinear, although we need to control the complexity of those nonlinearity, but if you want to make the relation of X with nonlinear, you can. We impose that the dimension of X is finite. In theory, this can be relaxed, but we don't think that makes a lot of sense because the high dimension structure is on the Y. We don't want the high dimension structure to be on the X. Okay? So what are the objects of interest? We want an estimator of the projection of Y on X, F, and W that generalize well out of sample. This is useful for macro and financial forecasting. This is related to the diffusion index method. Okay, so pi here represents a projection. Okay, so the projection of Y on X, F, and W. Remember, W is the variable that explains the dynamics of the U's. Okay. We also want an estimator for the covariance in partial covariance matrix of U. So we want the covariance and the partial covariance. That would be important for network discovery, for instance. Okay. And we want to conduct formal hypothesis tests on a high dimension structure of U. So basically, we want to test the hypothesis that sigma equals to sigma naught or phi equals to phi naught. Okay? There are many tests in the literature for sigma, not so many for phi. And this is in high dimension. And one thing that will be important, look, what are these quantities? That's the covariance of U. Okay? U is not observed. We are going to estimate U. And in order to estimate U, going back here, we need to estimate gamma. We need to estimate lambda. We need to estimate F. And then we have U. So in order to derive a test for U that will be applied to U hat and this test to be feasible, we have to take into account the uncertainty on the estimates of gamma and lambda and F. How we are going to do that we are going to do stepwise. We are going to first recover this term here. We are going to estimate gamma. After we estimate gamma, we are going to compute R, that's Y minus gamma F. And we are going to estimate F and lambda. After we have F and lambda, we recover U by U hat, and we are going to run the test on U hat, and we want to claim some result with respect to U, the population value, right? And this can be tough, okay? And this is one of the new results that we have in the paper. Okay. So what are the steps? First step, you have the axis. What you're going to do, simple. Take each one of your variables, run n OLS regression. Just estimate gamma by OLS regression. Oh, I want to have a causal interpretation for gamma. I don't want to do a projection. Well, instead of using OLS, use IV, use CCE, use your method of preference. Okay. Here we advocate that we are in a projection framework. We are going to use OLS. Okay. After the first step, we are going to have like the R hat, right? That, sorry, forget to put the hat on top of lambda and on the top of F. Okay. And we are going to write that R hat has a factor structure. Okay. And we are going to, and here is that, sorry. Okay. And we are going to run a PCA on the residual of this first equation. Okay. So we remove the effect of X by OLS. Okay. And then we run PCA. Oh, you don't like PCA? You want to use projected PCA, instrumented PCA? Not a problem. You replace PCA by your favorite method. We advocate the use of PCA. It's super simple and delivers the result that we want. Okay, but there's also this flexibility, and this will be clear in what will be the effects in the result in the theorems, the effect of changing PCA by any other method. Okay. Okay. In the end, okay, you run everything. You have the hat. So what we are going to do now? Oh, now we are going to run the sparse regression to estimate theta. So here's where we bridge things. So we took what kind of observable, we estimate like the dense structure, and then you estimate your sparseness. Then you may ask, but what if you don't have a factor model? What if you don't have any sparsity, just density? Our methodology nests these two cases, and the test that we propose for the covariance structure can allow us to guide if we need all these steps. Because, for instance, after running the first step, you can test the covariance matrix of R. For instance, you can test if the covariance matrix of R is diagonal. Because if it's diagonal, then there is no need, or if it's like block diagonal, or if it's very sparse, you don't need step 2. We can maybe jump for step 3. Or if you run after running step 2, you test the covariance matrix of U and it's diagonal, maybe in your step 3, you want to include just lags here. You don't want to include contemporaneous effects. So you can guide your method in empirical applications by running those tests. Okay.
Oh, Matardo, I think usually the Q&A is toward the end, but I think my colleague Dintao has a comment. I think it's probably important that Dintao, do you want to speak up to clarify this point?
I don't need to read out. It's very clear that Marcelo's first step, OLS, takes a very different perspective from the interactive fixed effect, right? Because you don't worry about the endogeneity of X.
Yeah.
To lambda and F.
Yeah. That's true. Yeah, that's what I mentioned, right? We are here taking a projection perspective. Okay. So basically, what if you want gamma to have a causal interpretation? So you need to basically, what does it mean? Is that you have to consider a dependence between X and the factors, which are assuming to be orthogonal here, right? In setup, right? So if this is the case, like in by 2009 and the run econometric paper, also, you need to change the estimation in the first step. Okay. What we show is that if you replace OLS here by the CCE of Pesran, which is a method that allows X to be endogenous, it doesn't change the convergence rate of the first step. Okay, so basically this will have no effect on the remaining steps. Okay, but imagine a situation where, for instance, you come up with a different method that will change the convergence rates of the first step. What will happen, and I'm going to show you in the theorem, that this will affect the convergence rates of the following steps. But we are going to make explicit this dependence. So whenever you recover the convergence rates of a given step, our theorems allow you just to plug in this new convergence rate in the following step and derive results, right? Because we make this convergence rate explicit in the results. But you're totally right. Here, we are taking a projection-based framework. It's not a causal framework, but the methodology can be easily adapted.
Thanks.
Okay, imagine that you want to do prediction. If we want to do prediction, we want also an out-of-sample prediction. We need to project the factor. Okay, because we are estimating contemporaneous factor. We need to impose a dynamic structure on the factor. So if we want to do prediction, we have a four step where we create a non-empty set of legs of the factors, and we basically we write a VAR for the factors, and the final model is something like that. The projection, the final projection of y will be the projection on the x. Projection here, see here instead of the factor, we are replacing by the projection of the factors on the leg and projections on the idiosyncratic term. Okay. One question that also appears when I present the paper: can we estimate this final model jointly? Well, I don't think so, or at least even if we were able to derive theory, it would be quite unfeasible to estimate everything, because you have a sparse estimation in high dimension here, you have a dynamic factor going on here, and you have this first term. To put all this together, I think it would be pretty hard. Of course, if you can do jointly, you may have, probably you have gains of efficiency, okay? But here, we advocate a stepwise methodology, okay? We are doing this in a system, okay? And we leave, if someone work out how to do it jointly, I'll be delighted to see. I think it's going to be a big, big challenge, okay? Okay, so the covariance matrix, the way we do to run the test is that we just need a consistent estimator of the covariance matrix. So it doesn't need really to be positive definite for us to change the test structure. So we show our results with the simple, naive sample estimator of the covariance matrix. Of course, disclaimer, this is not positive definite, but for our results, that doesn't really matter, okay? That's the simplest estimator possible. Okay, there are many others in the literature that people can use. I recommend the beautiful survey by Olivier Ledois and Michael Wolf in Journal of Financial Econometrics last year about the several different estimators for the covariance matrix. Okay. For the partial covariance matrix, we also use kind of a naive estimator, a sample base, but we need, instead of U, to put what we call V hat here, where Vij hat will be the residual of a lateral regression of Ui hat onto U minus Ij, okay, removing element I, element J hat from U hat, and running this lateral regression. We show consistency of these objects here. In the paper, we show that these will converge to the true partial covariance under some sparsity assumptions on the partial covariance matrix of the residual. Okay. And how we run the test? Okay, we want to test the hypothesis that sigma equals to sigma naught. It can be like phi equals to phi naught. It's the same thing. This is a high dimension object, right? And we need to do some Gaussian approximation bootstrap. So basically, we are going to define the statistics, okay, that be the max norm, the square root t of the max norm of the deviation between the estimated object and the hypothesized object, okay? And basically, we are going to use the bootstrap to make inference using these statistics. To run this thing, we need an additional estimator, which is called the epsilon hat, which is the long-run covariance matrix of the vec of UU hat. So we need a kind of long-run kernel-based estimator for a high-dimension object, okay? Where we are not using U, but we are using something with a hat on top to estimate. Okay, this is also a new result. But once you have this epsilon, okay, we can compute the alpha quantile using a bootstrap estimator. Okay, we're going to compute the alpha quantile of this statistic S star, okay, which is going to be based on Z star, and Z star is going to be simulated, okay, by a high dimensional Gaussian distribution with zero mean and covariance matrix epsilon hat. So we simulate these, we compute the quantiles, and we compare to the statistics that we have. Okay? So that's the idea of the Gaussian approximation bootstrap. Okay, what are the complications here? Why don't we take like the Chernouzikov and Coulter's results and just plug in here? Well, several reasons. First, we have time series data, so we assume that everything is alpha mixing here. Okay, so it's way more complicated. Second, everything is estimated, so we don't have U, we have U hat. Okay, so this makes our life miserable. Okay, so we base on Chernouzikov, Cheteritov, and Kato results, but we are generalizing them in several directions. Okay? Lots of estimation going on, so we have to control for the accumulated sampling error in each step, and we have to do this uniformly in I and in T. Okay, the inference is in a high dimension object with serial dependence, so we need this Gaussian approximation for dependent data. We need that sort of new West type of matrix in high dimension. Okay, our data is a strong mixing process. We bound things by Orlick's norms. Okay, I'm going to show you results for the polynomial case. Assumptions are basically the standard. I'm going to keep them. Okay, so these are sort of the type of results that we have. Okay, and the result can look very complicated because everything is very explicit. So this we put some bounds on the first step estimator. You may say, well, but that's not the usual OLS. We are running a lot of regression, right? Remember, we are running n regression, and n is diverging. So in the limit, we are running an infinite amount of regression. Okay, so we have to bound the error, the estimation error. Okay, and this estimation error depends on several quantities that we make explicit here. Depends on R, number of factors. But you say, factors, why the factors depends on that? Well, depends on that because it's linking all these variables. It's cross-section correlation. Okay, it depends on the dimension of the X, the dimension of how many variables we are estimating. Okay, depends on the number of regressions that we are running, and depends on the number of observations that we have, and depends on moments that T will come in our hypothesis on the moment. Okay, and then you may ask, what on earth is this calligraphic R alpha here? That's what the referee asks us, not only to make the result explicit in all these quantities, but allow us also to have the mixing coefficient of the alpha mixing process changing with the sample size. So you may have different mixing, or the instead of assuming that exponential decay for every series, this can change with the sample size. So they wanted us to make it explicit, the alpha mixing coefficients in our results. So that's what about this R alpha is about. If you assume that's the same rate for everybody, this calligraphic R becomes a constant. Okay, so this is the first step. So this is what we call the rate of the first step. Okay, so you can call this a ladder, Greek ladder, that will propagate to the other step. Okay, so what's the second step? Well, now imagine that the first step is omega, the rate. So this is OLS. Now replace for your favorite estimator, your ID, your CC estimator. This may change. So, but now we make it general, and we are calling omega. And this will propagate in the second step. The estimator of the factor space, the estimator of the loading space, the estimator of the idiosyncratic. You see that the omega appears here. If you don't have the first step, make omega equal to 0, this term vanishes, and these are going to get back to useful factor models. Some slight difference depending on the way we define H. Okay, but basically we recover the results in Jen Ching's book, right? On his chapter on factor models. Okay, we are using the exact notation as in the book. Okay, so then, of course, I don't want you to get all the bits and pieces here, but what's important that you have everything explicit, so you can play around with the omega, the first step. You can play around on the convergence, on how fast T grows with respect to N. You can play around with moment condition, like tail condition on your variables, right? On your random variables, and you can play around with also with the decays, the mixing decay. You can assume everything is constant. That will simplify a lot the results. Okay. The third step, you're going to get the U's and run the lasso, right? With this penalty parameter estimated by information criteria, for instance. Okay? Then you get this ugly result, but basically we have like here the bound on the thetas, right? And you see that this will depend. Now you have the estimation error on U that we call eta, right? And this eta will appear all over the place here on this constant, on this phi here. So basically we have a bound that depends on the sparsity degree, okay, that you have on the first, so this is very typical with the last estimation. Okay? The complication comes for this term here, phi2, where it depends on all these quantities, on the mixing coefficients, and on see here the convergence rate on the second step, which depends on the convergence rates of the first step. So we have this propagation. Okay? And if we take eta to be OLS, then we can simplify the result, and we can derive L1 bounds, uniform bounds on theta hat, on the estimation error of the thetas, that basically will depend on the sparsity and on the moment, the interplay between T and N, and this term here that complicates, because it's again the mixing part that we were asked to make it explicit. If we consider that everybody decays exponentially, this becomes a constant. Okay. And then we can have prediction bounds between the estimator, where we have y tilde is just like with population values, the prediction with population values, and y hat is the estimated values, and the bound depends on all the convergence rates. The convergence rates on theta, the convergence rates for the gammas on the first step, the convergence rate for the U's, so on and so forth. Okay, so if you change one method in one of the steps, these results won't change. What would change is what we are going to replace here, what's going to be rho gamma or rho theta, or things like this, right? But this is invariant to the method you're going to use. You just need these things to converge at some rate, okay? And then you can plug in here. We also have the results for the test. So basically, we show the test has the correct coverage, right? So they are honest confidence region. So basically this result here that's translating to plain English that we basically saying that our Gaussian bootstrap works and we can test structures on sigma head and on pi head, okay, in this very high dimension. Okay? Let me take like the last 7 minutes that I have to go to one of the empirical applications. I don't have time to go for the two. So I invite you to look at the paper for the second application. So the first one is based on factor models and network structure and asset return. Okay. So we have this data set that's monthly close-to-close excess returns on more than 9,000 firms traded in the New York Stock Exchange from 91 to 2018, have 326 observations. So you see that N is much larger than T. Our N is 9,000 and our T is 300, okay? And we want to explain the links between firms by looking at the return. So we know from finance that we should use a factor model. And there are many factors that are observed. So we are going to take like the 16 more common factors, okay? So this is the list of the 16 factors. Why 16, not 15, not 3, not 4? Well, we made a choice. This is just an illustration. Of course, you can play around with that. These are the factors. So market, small minus big, high minus low, conservative minus aggressive. So the typical Fama French style portfolio return. And our firms are grouped into 20 industry sectors. Okay, here is the number of firms in this sector. Okay? So of course it's difficult. We struggle how to show the results. So we decided that we're going to show for some sectors. Okay, so what this picture that you're seeing? This is a correlation result. This correlation estimate using nonlinear shrinkage for some sectors without doing anything, taking the excess return, okay, and computing the correlation matrix. But of course, all these things are very related. So if you just plot the covariance matrix, we are going to have a black square. So basically what we do is that we take like all correlations that are larger than 0.15 absolute value, we color it in black. If it's less than 0.15 absolute value, it's white. So that's what we have. But the idea here is basically, okay, this is a pretty dense correlation matrix. So all the stocks are highly related, maybe petroleum not that much, but the rest are very highly correlated, okay? Very dense. Okay? So what we are going to do? Well, let's remove the factors. Let's remove the 16 factors. Let's run the first step of our methodology. And that's what we get. You see that if you compare here, most of the covariance matrix got less than, right? So you can see like in mining, in food, petroleum, manufacturing, retail and financial was pretty clear. It's almost, I don't know if you can see it, but it's almost a line, a diagonal line here. There's nothing else, okay? So, but for others like utilities, there are still, and department stores, there's still some correlation. And also in mining here, there's many. So the factors were not able to remove everything. And you say, oh, maybe because you're misspecified the factor. So let's run the PCA on those residuals to see if, like, having these unobserved factors, we can remove more structure. And, well, not that much. In fact, we introduce more dependency. There's not much change. Doesn't seem to be working. Okay? So there's still some dependence, okay? But what happens to the partial correlation matrix? If we run the partial correlation matrix, then boom, we have diagonal. Okay, so most of the correlation vanishes. So there is some, you may think, okay, we have covariance, dense, you have partial, it's not dense, almost diagonal, there's something, some indirect link, okay? So what we thought, that's an industry factor. We tried the industry factor, same thing, nothing changed. So what we want to do, the third step, the shrinkage part, the sparsity part, will give us the answer, okay? So what we did, we took the idiosyncratic for each firm, and we run a lasso regression on the idiosyncratic of all the other firms, right? And here I'm grouping, so the number of non-zero coefficients of regressions of the mining sector on mining sector, food sector, paper, so on and so forth, okay? And these are kind of normalized by the number of firms that we have in each sector, okay? So it will give us like how much dependence we have of the idiosyncratic in mining, on food, and so on and so forth. So you see that almost blue all over the place, okay? And blue, it means very small fraction. So there are very little dependence of mining on all the other sectors, and the same thing for the rest, apart from one sector. That's what this yellow column here, and look at it, financial. So there's a kind of a financial factor, maybe you can call that, but there's a financial link, some firms from the financial sector being important to the returns of the others. We try, okay, maybe this is, so it's a financial factor. We construct a financial factor and it doesn't solve the problem. So it's not that there's a dense factor, but a kind of a sparse relation. And maybe because in the financial sector, we have insurance also. So it could be insurance. But the main result here is that the methodology was able like to uncover a kind of non-trivial link among those firms. We removed the factors. The factors were not enough to explain the network structure. So we need to use this combination. Here's where bridging the factor, the dense and the sparse model shows some gains. Okay, so that's what I want to show you. And there's a second application on forecasting. But let me wrap up. So we have this method to combine the two methods. So we have the best of the two worlds, like factors and penalized regression, new inference methods, and you can show applications in treatment effects, forecasting, network structure. So thank you very much. So please ask questions, complaints, comments. Thank you very much.
Thank you, Marcelo. Yeah, so now we enter this Q&A session. You can. Oh, I think Tony has a question. Oh, Tony, that's a long question. So
yeah,
I just ask.
I thought I laid it out pretty clearly. I like the general approach, and I appreciate the way you bridge the two camps, two traditions. My simple question is really, is it fair to interpret your stepwise procedure as kind of privileging the density model and then using sparse model to enhance density model? Is it one being the lead and the other is enhancer, or you have to regard it as symmetric? They are equally important. That's the gist of my question. It has implications for the latter part of my question. If this interpretation is correct, then your earlier answer to Dento's question makes even more sense. You can have a more general causal model as the first step, and then sparse model techniques could be bring in to enhance a causal model in a high dimensional context. So See,
It's a very nice question. It's the first time we got this question, and we thought about that. And you were right in a sense, because we have to start with the factor model, right? So in a way, we are assuming, okay, there is a factor model, but the factor model is not enough to capture everything. So we are, in fact, enhancing it. We are using more information, because the factor model will leave information on the table, and we are enhancing it by using what was left on the table to improve the method. Okay, so in principle, yeah, that's true. We have this kind of privilege to the factor model, because we have to do it first, right? Because we cannot do the other way around. Because if there is a factor model, we cannot do the sparse regression, because the sparse regression will be meaningless, okay, if you have the sparse term. So we have to do it in this order. Okay? One thing that we can say, oh, but what if you don't have a sparse model? Because then, because for our results, we are assuming that there is a strong factor model. Okay, so what happens if you have a weak factor model? Or what happens if you don't have factors at all? Okay, and if you're running this CCA, who knows what you are going to get? So that's why we have also the testing structure, because you can use the testing procedure as a kind of diagnostic tool. Because after running the first step, you can, for instance, do what I did in the return exercise that I've just showed you, like ad hoc analysis, but we also run the test to check if the covariance matrix of the residuals was dense or not. So if you don't have any factors, after removing the axis, after removing the first step, okay, you're going to have a sparse covariance matrix. And then you can skip the factor at all. Okay, and move to the third step. Okay, so the testing can help you not to give privileges to the factor model. Okay? But if you don't run the test, you just run the procedure, you are implicitly assuming that yes, we have a factor model, but the factor model is not enough to model the data. We need more. We need the sparsity. We need the third stage. We need the lasso regression, and we are going to enhance the factor model. And of course, you can do this with a causal interpretation that you are kind of enhancing. Usually, the causal stuff ends on the first step, because the interest, okay, is on the gamma. You want the causal effect of X on Y, controlling for a potential factor structure in the error. Okay, so usually you end up, but we are giving like, okay, you can do this, but you can even try to uncover what's in the error. So you estimate your causal effect gamma by method, Pesarun method, or you could come up with an IV method, right? And then we try to enhance it by also looking on how things work, like maybe causal networks, right? If you want like to interpret the links among the idiosyncratics in a causal fashion. So this is also possible. We don't touch causality in the paper because the paper is way too long. But a nice extension is like to have a version of this paper more causal oriented. We have the counterfactual paper, but it's also causality in a synthetic control framework. Okay, so in the end of the day, it's still a prediction model that we are using to conduct causal instance. We are not estimating causal parameters. Okay? But it would be interesting to have a causal version of the paper.
So we have Wen Hui, I think maybe he's a graduate student. He has a question, when you remove the strong correlation caused by the strong factors, there may still exist some weak correlation, and sometimes you can use a few weak factors to describe these remaining correlations. So the question is, what should we expect to use in addition to the strong factor, the weak factor, or these idiosyncratic components that you mentioned?
Then it's a matter of taste, right? In my view, when you go to factor model, I prefer the factor model to be strong, and weak factors for me calls for a sparse regression. So basically, if you have weak factors left after you remove the strong factors, what we are claiming in the paper is that we are going to use a sparse regression to model this relationship and not estimating a weak factor structure. Okay, because to be honest, I think we may have an identification problem. If you have, is it a true weak factor, or in fact is a sparse regression, a sparse relation that we are kind of approximating by a weak factor? What's the truth? I don't think it's possible to distinguish between these two. Okay, so there are two ways of modeling sparse relationships. Okay, so I think that's a way more complicated problem, okay? And I don't think there will be a solution. So our take here, when we bridge, we're bridging density, so you're bridging strong factors, okay, with sparse. If you have weak factors, this goes into the sparse stuff, the sparse component of the model. Okay, and we had this type of question appears from time to time, and we had this discussion with referees. This is a paper about strong factors and sparsity. Weak factors we call sparsity, and goes into like the third step. But it could be something to discuss in the future. What's a sparse model vis-a-vis a sparse regression? To be nice to have some insights on that. I don't have any now.
Okay.
No.
So
the answer that with the sparse assumption you have the estimation of the factor mod stuff. No, not at all. Because then you can use like biennial result that if we have moderate correlations on the idiosyncratics, everything goes through, right? So we are just under the biennial assumptions we don't need to impose sparsity to get the second step. The sparsity assumption only comes in the third step.
Okay, Marcelo, I have myself has a question relating to I think the third step, right? When you have this idiosyncratic component, you have this lasso type of regression. But I mean, of course, the theoretical property aside, my question is, would you improve the performance if you consider some machine learning methods, like the deep neural network, right? I mean, so essentially, you want to recover this maybe with kind of the nonlinear or relationship of another related thing is you only include the other unobserved use in this model. My question is, why not consider this W, because the information is already integrated in this step? Or I mean, we only
let me show you. Okay.
Yeah. So that's two questions. Thanks.
So for the first question about making other than lasso, Jianqing has a brand new paper that you can Google it on archive. I think it's deep factor model, something like that, right? Where the third step is a deep neural network here. Okay. So he has done this with some PhD students. So I haven't read the paper yet, so I don't know exactly the framework, if it's all IID, it's not IID, and what exactly he had, because the brand new paper, I have to read it, but he did that, okay? And so yes, it's possible. to make it this third step very flexible, and probably it will help in some cases. Okay? The W's here, you see that what the W's are. The W's, we can have legs of everybody and contemporaneous of all but I, right? So in fact, all the information here. What exactly you asked if we can include on W, the X? Because we already projected on X, right? So we hope that we don't have anything here. One question that appeared once to us is that why don't you put, instead of putting the X on the first stage, you put the X on the last stage. You put the X on this second regression here. Well, it's possible. I think it, in some case, for the case of the example of returns, I think it's unnatural, right? So you want to first regress on the factors that you observe. So we believe that having it here is better than having it here. Of course, if it acts as large dimension, it complicates. But in the applications that we have in mind, what's large dimensions are the Y's and not the X's. So the X is kind of a fixed dimension. Of course, this was a model choice because it was more in line of what we see in typical applications.
All right, thank you very much. Okay, so any other questions? If not, then let's thank Marcelo again for this very interesting.
Thank you very much. It was a pleasure.
Thank you. All right, thank you, everyone. Yeah, so now this webinar will end here. Thanks.
Okay, have a great day.
Night.